All right. So how about we
So
bring in our next
l-
guest?
I think we should. I think we should.
Hello. Welcome to the show. How about you introduce yourself?
Hi, thanks for having me here, Ryan and Wine. Yeah, my name is Jiang. I'm coming from Zilliz, Milvus. I'm leading the developer relations of open source hardware database Milvus, and also the responsible for the solution architecture of the fully managed version of it called Zilliz Cloud. Really happy to talk about generative AI, powered search, and information retrieval in general.
Awesome. So thank you for being here. So let's talk.
Yeah.
Tell us a little bit about your company.
Yeah.
Oh yeah. So yeah, we're a Zilliz, and our main product is called Milvus. It's an open source vector database that we are maintaining and we created several years ago, a while in the back. And since it has been a hell of a journey, we kind of invented the term vector database before there was a term vector database. At the time, that was called the retrieval infrastructure for machine learning generated embeddings. It's a very geeky term that only a few people like in Google and Facebook they know that. But over time, this embedding or machine learning model based retrieval it has gone more and more popular, and this concept vector database has also gone viral. Probably along the same time that ChatGPT got being used by anyone rather than just a niche community of researchers. So since then, yeah, there has been a lot of change in terms of the adoption, in terms of how people see information retrieval and the whole infrastructure that powers it. So I think we are from a traditional perspective, we are the pillar of information retrieval, like the database that you can stuff information into it. The information is represented as a bunch of numbers that people really cannot really comprehend, but machines, they are good at understanding it and using it to find semantically related stuff to you. That was kind of the traditional way of seeing this piece of infrastructure in the tech stack. But over time, people got really excited about generative AI. So I guess the story around this has changed a little bit. So people say, this is a memory for agent. Right? This is something that you just stuff in, and then you can find the information. And somehow, a large language model can rephrase that in a human-friendly way. So suddenly we become the pillar of RAG or retrieval augmented generation. Like if you are dealing with any chatbot, asking questions about softwares or asking questions about the relocation policy in your company, there's probably a vector database behind that powering this kind of search and give you related information so that large language model can use that and then just act as a human being, as if it was a human being, and then answer this question for you. And we are that vector database. But we are not any vector database. We are the scalable and cost-effective vector database that's built for production. There's a lot of vector databases if you are in this domain. Some are easy to use, easy to get started. Some are like relatively complex. We are those. We are on the like sophisticated side of the spectrum. Our architecture is fully distributed. It got a lot of components so that we can handle this trade-off between different components handling different types of workload or different parts of the workflow, so that it gives flexibility in terms of scaling up in the production. And we have worked with a lot of great users in the open source community and also with the paid customers for the fully managed version. And we scale them, we scale their workloads, search workloads from say 1 million vector to 10 billion vectors. So scalability and dealing with serious production and mission critical workloads, that's our strength, and that's what we are spending a lot of effort on.
It's impressive.
That's really cool stuff. Wow. So with Gen AI models, right, are like just generating massive quantities of embeddings. And it doesn't seem to be slowing down. So how are you guys helping to sort of manage that onslaught?
That's a really big question. Well, usually I would like to look back to the history. So information, the blowing, the kind of explosion of information, that's not a new thing. It actually happened once in the past, like around like after dot-com boom, there was like a lot of information showing up in the on the internet, and then what came to solve that problem was Google. Right? So there was a search engine that helps you find information from find the useful information from an ocean of web pages and other types of content. So that thing has actually happened once, but this time it's getting even worse or better. In terms of a business, that's better, but in terms of a technical problem, that's worse, because large language model can just generate a lot of information in a very short period of time. There are so many people asking questions, and there are like a lot of models deployed anywhere generating answers to that, and that becomes information as well. It probably materialized somewhere, say on the internet or in your in some particular applications walled garden, right? So or there is, say, image generation models that can generate photos with a lot of creativity, which is faster than what you can do with an iPhone and clicking on the photo button. So yeah, there's a lot of information showing up after this generative AI wave, and our resolution to that is, of course, we build more powerful systems so that we can store that information. But also we were thinking from another perspective, which is how valuable those information are. So traditionally, we are mostly dealing with highly valuable information that if you want to do a search query, you want the search query to return within maybe 10 milliseconds, or worse, like for RAG, because you need to spend a few seconds on generation, probably 100 milliseconds, that's fine. But still, that's like on the millisecond level, right? You want the result now, immediately. There was a saying with Google, like if the search is slower by 10 milliseconds, then there's like $10 million being lost within an hour or something. That's not a joke, because I work for Google Search, so I know that's actually true. We do care. Back in that time, we do really care about the search latency. So that's or it's a recommender system. Say if you open some application on your phone, and then you expect a news feed to show up immediately, right? You cannot really tolerate a running circle of something running for even 500 milliseconds. That's really hurting the user experience. So all of those are online use cases, and the vector database, especially Milvus, the one that we are doing, that was designed for this kind of workload, so that on a high level, it kind of stuff all of the information into very expensive RAM, so that it can be retrieved really fast. Say if you are using HNSW, indexing algorithm is pretty much sending all of the information into RAM, so that, say, if you have a billion vector, that's probably several terabytes of data, and you need several terabytes of RAM, and just to serve this information on online fashion. But a lot of times, for the information generated by a large language model, it's probably some kind of archive, right? I don't want to say garbage, but it's some kind of archive information a lot of times. You don't really need to find that information within 20 milliseconds. Probably within 5 seconds, that's fine if you want to explore with this information. A real-world example for that is actually large language model training. Because in training, you need trillions of tokens. That's a lot of information. And also you need to do some curation so that you can make the model perform as you wish by curating the data to teach it, right? It is pretty much it's kind of similar to your training data in some sense. So to curate the data, you need to kind of find information that you want that's pretty much retrieval or search. So in that kind of workload, it's dealing with a whole lot of data, but that data doesn't need to be returned within 10 milliseconds, because you are kind of doing this offline tidying up or offline processing of the information. Another example is in autonomous driving. So those electrical cars, they collect a lot of information from the road, and let's say those are kind of frames from the videos. Those images, there could be easily like 10 billion, 100 billion of such images. And to train a better autonomous driving algorithm, like, it's better that you refine the information, or sometimes you want to find some corner case, like this particular road, which looks really weird. And I want to find this photo of this road, of this crossroad, and maybe even in rainy weather, like in extreme weather condition. You want to find that information by specifying the semantic in your query, but you don't really expect this query to return immediately because you are not a consumer. You are probably a data scientist dealing with a lot of such queries. You're okay with 5 milliseconds or maybe 5 minutes of search latency, right? Because you are doing this in batch fashion. Or sometimes it's even a machine doing this. Right? So you probably want to process 1 million such queries within a day, but for each query, it doesn't really need to take a lot of time. So for those kind of offline workload, it actually deserves a different design of the system, not the same design that we built for the online query use case. Right? That's too expensive. That's too good for this use case. So that's another thing we're working on, which is called vector lake, which is kind of borrowing the idea of lake house. Like for data warehousing, those are not so valuable data that that deserves a relational DB like for online serving. That's too expensive. So that people invented this concept of warehouse or lake house. And that same idea really applies to vectors as well. For this kind of interactive search or offline search, really we can just stuff the information into, say, object storage and then build a query engine layer on top of that. So instead of fitting all of the stuff in memory ready to be served, they can be retrieved. They can be kind of brought up from the object storage to the query engine layer and then processed and then returned within, say, 5 seconds or 30 seconds. And that can save maybe 100 times of money in terms of the serving cost.
Yeah, so we actually had an interesting question come in. It says, how do you handle possible state data with caching?
Stale data.
Stale data, sorry. Yeah, my
caching.
glasses.
Yeah. So how do you manage caching stale data? It's like the question as old as time.
Yeah, that's really a good question that's coming from the operations in production. We also got a lot of questions like that. I think a few points, right? So depends on how stale the data is, basically. Right? Let's say if the data is still valuable enough that you want to serve to the users, whether it's 100 milliseconds, 500 milliseconds, but it's serving. It's not like I will get back to you tomorrow, right? As long as it's not that case, is we still see it as serving data, and the serving data you can store all of them in memory if you really want to say sub 10 millisecond latency. But if you can tolerate 100 millisecond or 200 millisecond latency, you can use disk. If you can tolerate a little bit more, we have this thing called tiered storage. It's available in both Milvus and fully managed Zilliz cloud. So this tiered storage is pretty much like multiple layer of cache, right? So the RAM, most expensive RAM is the top layer cache. It doesn't really, it cannot really fit all of the data. It can only fit a small portion of the data, but those frequently accessed things, you can store them in this. And then like below that, that's cheaper SSD, but still way more expensive than object storage, which is really code. So that we leverage these 3 different layers of storage to store the information. And there's a caching, there's eviction mechanism, right, to make sure that the frequently accessed information is in the top, like upper layer in this stack. A typical example of this application of this is consumer-facing products. Let's say for like smart note-taking tools. Right? So for that tools, a lot of people, they store a lot of information in their notebooks, but they will never use it. They will never retrieve it. but there are some power user who has maybe not as much data, but they frequently use this product and they interact with their historical information, right? So you want to place those power users or frequently accessing users to the top layer of the cache, like RAM or SSD. And then there are like really cold storage, like object storage, that's really cheap. And AWS S3 offers a great product S3 that can store a massive amount of information with really low cost. And those information they can be stored in S3. And only when the user access this information will those data be retrieved will be kind of bumped up to the more expensive RAM or SSDs to be served. But usually those users they don't really access this data more than once a year or something like that.
Awesome. That's super cool. So I think you have a demo for us. Is it possible we can take a look at that?
Yeah, why don't we go to that? I mean, talking is too abstractive. It's like when we especially in the earlier days when we kind of introduced the idea of information retrieval and vector database to the user, they were always like, what, a database can do search? That sounds unlikely, right? Or what is search? I was usually using some examples to illustrate the idea. So this is so far my favorite example, which is, let's say you have 100 million or 1 billion interesting images, like a massive amount, maybe it's a Flickr or something, right? There's a lot of photos that you have to. And sometimes you want to find these photos by semantic. And traditionally what we did was, you search by text, and then those information, all of the photos, they are labeled with text. So it's pretty much like keyword mapping. That's not interesting. So what vector search empowers is search by semantic. And the semantic, I guess the basic version of this is that semantic can be expressed by another image, which is, say, this red car, right? That's an image expressing our search intention. But what if I want to actually find something else? It's similar to this one, but actually slightly different. So I want to find something similar to this shape, like a sports car, maybe a convertible, I don't know, but in blue color, right? So there are awesome embedding models that can do this by taking both an image and a piece of text as input and kind of fuse the search intention behind those two pieces of information into one single vector, and then search among an ocean of other vectors, an ocean of other images represented by the vectors, generated from the same model. So this is what it unlocks, right? You can search with your intention and kind of adjust the intention expressed by this image by some text, right? I don't want the red color of the car. I want something similar with blue color, or like, I mean, this is not a fake. Let's try yellow, or just name any color that you want. So as long as this corpus has such information, it can actually retrieve. Right? You can see, all of those, they are sports car, they're with yellow color, but the lower ranked, the ninth best or 10th best, they are actually not technically yellow color anymore. I think this model doesn't always do the best, so that you can also re-rank by using large language model. But anything before this, that was done purely by the embedding model and vector database. So vector database is the facility that can store the vector information and then retrieve this within really like strict latency expectation. And Milvus, I think so far, we have put a lot of engineering effort into this to make sure that it can reliably return the result within 10 milliseconds, right? If that's what you want. But let's say if you want 100 milliseconds or even more than that, and you don't want to pay as much, Milvus also provides the flexibility. Same applies to the fully matched version of this as well. The other example is I just want to quickly show another kind of interesting query. Say, I want this in a construction machine, but I don't want the real construction machine. I want a toy of this. So by searching this, again, this thing together converted by embedding model into a vector, and then search a billion vectors in your corpus, and then return the top 100 or top 10 to you. Right? So as you can see, the top ranked results, they are actually toys. This one, I don't think technically this is toy. This is probably a real vehicle in the snowy weather. Right? So again, it doesn't always do the best. If you would like to pay way more cost, way more like latency and compute power, you can use a large language model, a vision language model, to kind of read each single image and then re-rank it. And then, in this case, it does give slightly better results. And also you can what if I just curious about snowy weather? So I want something like similar to this, but also in snowy weather. As you can see, this time this one got bumped to the first choice, and all the other choices I think they're pretty decent in terms of matching the semantic intention of the query of the search.
Yeah, no, that's really impressive. It looks like we might have lost Brian for a minute. That's okay. It's just you and me now. That's really cool. No, I love how this is really like it's a powerful example of vector databases. I haven't seen it kind of so clearly and cleanly displayed. Nicely done. I like it.
Yeah, there's actually another quick example I can show, which is more, I would say, more popular among the developers, or you have probably seen this like so many times. Basically, it's an AI bot that can, you can ask questions about it. In this example, let's say, we recently released the latest version of Milvus 2.6. It got a lot of great features. This AI bot, it can read through those, it can actually search through those software documentation, which introduces about features and use like all the usage instructions, and then return the result, a really grounded result backed up by the real content in this corpus, rather than just making up things by the large language model. For example, this case, Milvus 2.6, it released a few great features. For each of the feature it mentioned, it actually will give you a reference, which is the software document from the search result. Right? So those things, I think it has been used really frequently by a lot of developers. In this case, we actually have so many developers enjoying this chat AI bot, so that they don't need to use Google to search the software documentation of Milvus. And also they usually get the result they want.
Nice. And we only have a few minutes left. So one of the things I did want to make sure that we had a chance to talk about, not thinking about like comparing yourself to other vector databases. Like you guys stand on your own, you are your own thing. But there are options. There's plenty of choices. There's a lot, as you mentioned, there's other vector databases around. Why is a customer, like when a customer runs into X problem, you're the obvious solution? Like what are those types of problems that really lean into your strengths?
That's a really good question. I would say from our operations, what we see is that when the customer enter production and then they are serious about this workload, it's no longer a demonstration of what vector database can do or search can do for you in the generative AI space. When they have, not 1 million vectors, they have 100 million or even more than that. When they have not like 2 queries a day, they have 100 queries per second. When they have that kind of serious production workload, that's when they really like us. I mean, they probably have liked us before that. I am kind of cocky sometimes, but that's when they really, start to become friends with us, because they know, there are not so many options on the market that can actually do this. There's probably 100 options that you can use to build a Twitter demo. That's true, right? So no argument on that. But I would say production, scalability, and sometimes also about cost, right? So if you are dealing with 1 billion vectors, you need terabytes of RAM. which is probably I don't know, like $1 million, $5 million a year of cloud bill, right? If you're dealing with that, you do care about the cost effectiveness, right? Can I save the cost by 3 times? Sorry, AWS. I don't want to, do bad with your revenue. Sometimes the customers they do care about their money spent on the infrastructures. That's also what when we do good. For example, we have this RabbitQ, this really like crazily good binary quantization algorithm that can save 70%, 50% of the RAM cost, and still offer the same kind of search quality to you. Right? So we put effort on those kind of research. We work with the academic researchers, and we productionize that into Milvus and Zilliz Cloud. I would say those kind of things that someone operating a production level database or search engine, what they worry about, that's where we do good, and also that's the reason why users really like us.
No, I love it. Like to me, it's the practicalities of production scale, like full stop, and that's really cool. Because like you said, there's lots of options, and lots of people are doing really interesting work in this space. But if you're dealing with 100 million queries and massive scale, you have to be very thoughtful because it can get out of control quickly, operationally, expense, whatever, right?
Yeah. And here at AWS, we love to see customers' bills go down. So like it's not a thing. We don't want to go up.
No, it's better. It's better. Yeah.
Thank you.
Yeah, no, we want our customers to get the absolute most out of every penny they spend. We really do. All right. We got a minute left, 2 minutes. How can our listeners get to you? How can we find you when inevitably we have a massive problem and you're the ones to solve?
Yeah. So the most, like, if you can bring up the screen, the easiest way is go to milvus.io. This is the website for our open source project. And also zilliz.com if you want a fully managed service, but you can also just click on this and use it. And if you want to, we are human beings. We're a real person behind this. We're not robots. So if you want to talk to us, you can actually sign up for the office hour or just join our community. So on the top there's community, more channels. We are on GitHub if you want to report issues. Discord if you want to chat and ask questions. And also ambassador program if you want to join the community and help grow the Milvus community by yourself or in your local region. And lastly, if you have a question, or if you want to talk about your use case, you want to get some advice on how to productionize your vector search, you can book a Milvus office hour. We have quite a few sessions every week. So those are ways to get in touch with us.
Thank you. That is awesome. Thank you. Thank you for joining us, listeners, viewers. Thank you for viewing us. Brian, thank you for co-hosting.
Thank you.
Thank you both for having me here. I'm really excited about the questions being asked by the audience, and also you guys. Really happy to share, more about Milvus, and connect to me. And my name is Jiang Chen. I'm pretty active on LinkedIn as well. Just search for Jiang Chen, Zilliz, or Milvus, and let's get connected.
That's great. Thank you. Well, to our listeners, to our audience, thanks for joining us today, Wednesday, from 8 to 9 on GenAI Live. We've had a great show. We hope to see you next week.